we are waiting for more people, right?
You said wait to get into?
Yeah.
Okay.
Hello. What are we missing? Queen. Kevin. Yes. And Gage. Is not coming. Let's wait until they come. This is from previous year, just discussion of possible research projects. Like toxicity of inorganic substrate for cell membrane. Someone thought, like, this is not a polymer. Those are just through dispersion forces they stick together. But it's not a true polymer.
Why is the screen blinking? I noticed that.
I don't know. I do not like it, but tech support didn't.
They couldn't fix it? Oh.
Or they didn't decide to go ahead and fix it. Yeah, please take some fruits.
There's two copies clipped together in there.
Oh, okay, okay.
I tried to keep it all in one place.
Uh-huh. There was something with the...
I mean, it's completed, right?
Done?
Oh, we have work to do. We have lots of work to do. I say we as like who.
Okay.
So I'm not alone. We're trying. We're trying.
Well, you're still working on it?
My crew.
You ran through?
My crew, or our crew. We're trying to-
So let's count 1, 2, 3, 4, and 5. Yours. 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this something.
It looked complete, right? Like that was everything that you needed?
I have completed the homework myself and will distribute it as an answer key.
Cool.
Okay. Did you print your homework? Can you quickly run and print it?
Oh, yeah.
We need a printed copy right now. One, two, three, 4, 5, 6, 7, 8, 9. And Queenie is coming, right?
Yeah.
She's probably printing. So I'll just entertain you with stories before we are waiting. It's really needed to get through practical skills, and since this semester is unexpectedly short, we are like about 3 weeks shorter than usual because of snow and because of conferences. There is a little speed up and acceleration, so please consider it with understanding. So if you are suffering a little bit from the long homeworks, it's because of the information and program is a little squeezed. So there will be 2 more labs before you do presentations on using WASP and before starting the projects. and squeezing all skills on new software in 3 labs is really tense. So it's I miscounted. I didn't count it that there will be a break. I hoped very much to do a class previous week. So we will go through regular class material as usual, but practical skills are really needed and we need to complete them. So as soon as this couple of gentlemen will come back with their printed work, I will distribute homeworks back to everyone, but not to the original author, but to someone else to appear along with grading key, and you will just compare and put grade and add together all points. So just try to be generous and give benefit of the doubt and exaggerate completeness as much as you can. So what we need to complete in the lab tomorrow and next week, if you're interested, or someone was asking what is VASP in the wave language, right?
What is VASP? Yep.
Good. You know what is Gaussian?
I know it's 3D modeling and you can get some...
Modeling? No, not 3D modeling. It's Gauss-U for 3D modeling. Gaussian is just to convert a set of coordinates into a set of energies, right?
Coordinates into energies, okay. Yep.
Right? And there are a lot of alternative pieces of software that do the same.
Yep.
Right? So VASP is one of them. And each of pieces of software have their original different format. Yep. So right now we all are experiencing a little pressure because VASP is not super user friendly, but later on you will see that like it's not quite easy to do things like that on Gaussian, right? It may panic, complain, and reject to cooperate. For VASP, it's like normal stuff. So later on we will discuss projects. You select what you would like to do, and then you will select which software matches your goals better. Does it answer your question?
Yeah.
Partially?
Yep.
Okay. So last week and this homework, we all did play, at least those who completed homework, did play with models that look like molecules, which are covered by vacuum from each side. Tomorrow in the lab we need to use full strengths and benefits of VASP, which allows for periodic solids. And some of you already got pleasure of setting up boundary conditions with these 3 parameters. So we'll take a couple of models which really need periodicity, like thin films or nanowires. Like this one is thin film, right? So it is periodic in X and Y, and it has a surface in Z direction. We also need to quickly get through orbitals and absorption spectra, and I think periodicity, orbitals and absorption spectra can be fit into tomorrow lab. Then I'll design some maybe a little less challenging homework, but still we need to practice these things. And then for the last lab there will be 3 remaining things. Well, there are many things that one may need for this versatile use of the software for your benefits, but 3 pieces are for another week are so-called dispersion curves, dependence of energy on momentum, the exact calculations of anions, cations, and excited states, and the most pleasant, spectacular, and useful part, the heating molecular dynamics and movies of molecular dynamics. So we will do it in 2 weeks. So tomorrow we'll do periodic boundary conditions, spectra and orbitals, and next week dispersion, anions, cations, and molecular dynamics. What are we missing? There is one, subject number 4, to do either next week in 2 weeks. The open shell, alpha and beta spins for magnetic materials. And then we'll be done, yes?
Yeah, so like with the project, I understand we're choosing, but
I will offer a list, and you can already send me what is your project, so I'm including into the list distributed. You will put
yeah, are we saying just you want us to choose a molecule and then just do all these different programs on it, just to get different
yes, but
values?
until so I just listed things. Probably I should write them on the board.
What does it put it on the PowerPoint?
Wait, too much for me.
He was kidding.
It's fidgeting, that's why.
Open shell. Open shell. What else? The dispersion. Anions, cations. So it's in 2 weeks, and tomorrow periodic boundary conditions, absorption, and orbitals. So before we go through these materials, it's a little too early to speak about projects. Right?
Yeah.
Excellent. I can take it.
Oh, I need to take the load.
I'll take a look at it. It's all.
It's the whole this.
So you didn't format it as.
Not yet.
Okay. Okay. So after we complete this subject in the labs, it will be reasonable to think and discuss the subjects for research projects. So before we get through these practical things, you may not recognize all strengths that you have. And with the things, especially with molecular dynamics, you'll be able to get through much broader range of processes compared to what you ask right now. So not only electronic configurations and basic descriptors, also some processes.
Thank you.
Okay. So yes, please, let's chat before Kevin comes.
Okay. Can we still finish this homework and send it?
No, there will be another homework and presentations to make up the grades, but right now we will start grading homeworks right now. 200 points maximum.
I mean, I did, but I feel like I'm still not solid on it.
Do not worry. I was already telling to other class attendees, the program is a little squeezed compared to normal because this semester is shorter than usual because of like snowfalls and conferences. Excellent, thank you. So I hope that no one here in class is super sensitive. Give me a little sign if you want me to like scratch your name so that your classmates do not see it. Okay, if you are not, then I'm going to do the following. Everyone will obtain 1 copy of a homework and 1 copy of a grading key, at least for the first part. Let's give 1 point for red and like 10 points for 1 point for black and 10 points for red questions, right? And then just compare it with the answer key give points to those whom you are grading. Try to be generous. Give as much as possible grades. Give benefit of the doubt. Right?
The red one is the
And,
points, the black is 1 point.
give me a sign if occasionally I'm distributing your own work. I'm not. Sometimes I miscount.
See, I'm confused because I thought that when you circled it red, those were the priority ones we need to complete. That's what I got
Wait,
confused on.
let me concentrate on distribution.
Okay, sure.
Not medium, right? Okay.
Huh? Not yours? Try to be as generous as possible.
Okay, question. You said-
I'll go over the answer key right now with
Okay.
publicly. If your question was about the answer key.
Well, actually, it's about the questions we had to do. You said the answers to question red are mandatory. So I did the mandatory ones. I didn't do the ones in black.
Therefore, they are order of magnitude different.
Okay.
Getting only red will give you the full credit.
Okay.
It's just a make up if you're not sure about.
Okay, sure. Got it.
Is it visible enough? Okay. I'll if you know what to do, if you just.
No, red or 10 points for black. So, see, this is red, so all this would be 10 points.
Black.
Okay, so the ideally such work is much better to type than handwrite. So these directories are made in order so that one can log in and check if things are done correctly. So where you have original thing on of the perovskite cluster. Okay, some were to work on perovskite cluster on the NERSC Quarry computer.
Why did the screen keep blinking?
I am not happy with it as well, but I do not know how to fix it.
I'll make it work.
And you have the copies. You do not need to. I'm showing the same document I have distributed, so do not worry. So some of you did have questions on directories.
Yeah.
So what I did, I logged into the NERSC Quarry cluster, and you all know how to do it, right?
Yeah.
Then went to the class subdirectory for me as a person, And then I made another subdirectory for this perovskite cluster. And then I make change directory to this perovskite cluster, and then I am located in there in this green stuff. And then when I need anything from the photon, right, I do SCP from my username photon address where I have previously created something related to this project, space, and then period, meaning to here. Here I do it once again. SCP secure copy, user, host, address, and everything .xyz space period. So there is an assumption that geometry is already created there. Now, where did you take the initial geometry? Well, everyone is welcome to do it maybe by Gaussian. I drew it by Avogadro because it saves in XYZ. And then I run it with Gaussian, assuming that I was doing previous homework. And then convert it from Gaussian log file, so -I, Gaussian 09, name of the log output, XYZ, and then file XYZ. And then I sorted this file into file named postcar XYZ. The name is unique. If I would assign a different name, the next code would not work. And then I manually edited, went inside by this ugly API program to see that it has a format of number of atoms, then empty line, and then Cartesian coordinates. Then I did run this rotate XYZ and provided the 0 values for angles. After that, there is a run of the code that converts. So this rotate code creates this tinker format that we do not need, but it is intermediate. So we run this tink to wasp code. So this is input file for this code. This is output file. So after space, we specify into which file we funnel the output. And here are the adjustments along X, Y, and Z. So like 8 is good number, but I decided to use 7 to make calculations a little quicker, assuming that little error will not hurt. Oh, and this one is red. I'm giving myself +10. +10, right? Here, +1, +1, +1. Right. So do the same to your peers, and give benefit of the doubt as much as possible. And so after this tink to wasp, it shows how big the cell was without adjustment and how big it became after adjustment. Copy paste postcar for the perovskite cluster. So it shows elements, the size of the unit cell in Cartesian, number of each element, and then fractional coordinates. Least amount of vacuum you have added in each direction, 7 along each. Least result of the command grep pb podcar. So without creating podcar file, the wasp would not work. So before doing this operation, one needs to concatenate potentials from repository to the podcar file. I do not count on my memory. On each system, these potentials could be located in different place. So on the NERSC, I can type module show wasp, and it shows directories to all things related to wasp. So the potentials are located in this green stuff. Global, common, blah blah blah, pseudo potentials. I'm not reading it. I'm just copy pasting. And then after copy pasting, I'm doing this concatenate, this address for potentials, then selecting element bromine / hot car, bigger hot car, and I'm selecting bromine cesium lead because it is the order that I do see in the postcard file. Bromine cesium lead, right? Did I miss to give myself any grades? Okay. +1. Then there is a potential place for error. For some elements do have indices. Like there is no pure cesium. There is cesium with SV corrections.
What's
and
SV stand for?
we are not discussing it right now. But there are different approximations. But for cesium, it's only the approximate is available. So it is the only one available for cesium, so we are using it. And after doing this concatenation, we should have a healthy pod car. So if I practice grep PB pod car, I get the record for bromine, cesium, and lead once for each of them. It means it is healthy. Then report used value of NSW parameter. Well, before reporting it, we need to copy the in-car from template to current directory. Otherwise, we will not be able to run VASP, right? So in the binary, there is an in-car geometry optimization space, period / in-car. So we create copy of the in-car. There are some values by definition, and you are free to modify them as you wish and see what are the consequences. Yes, please.
The first one doesn't work.
Which one?
Like after 9, number 9 CP, yeah, it doesn't work.
Read my marker.
After number 9, like after number 9.
Oh, here.
Yeah, the first command doesn't work.
CP. So let me write it because it cannot be seen here. CP space tilde / binary / k
Because
points
even when you were showing us in class,
space period.
you said it.
Huh?
Even when you were showing us in class, me said it that he tried it out and it did not work. I also tried it while
I did it this morning. I completed homework myself to make sure that I'm not doing.
I don't know why.
Well, let's do it in the lab when we will do next round.
Okay.
Tomorrow in the lab, I will be circling and helping everyone to make sure it works. Yes.
Does it have to be one of those things where you have to do it like all at once, and then like after you get that car file or hot car, then the next thing is K points. Like it has to be all within.
No. You need to have 4 files before things will run.
Yeah. So
Before you create this K points in car, pod car, and post car, you cannot get out car.
Yeah, I get that. Yep. With the K points, like, can I create the postcard and then stop for the night and go?
Oh yeah, absolutely.
Well, yeah, but the issue is we're having issues with that. Where we're not thinking. If we were to stop doing what we're doing and then come back on, we'd have to restart completely, keep going. Specifically.
Well, you do something, then you log off.
Yeah.
And then you log in again, and the files in your directory will not disappear.
Well, like with post.
Unless some of the people who have privileges to your account intentionally delete it.
Okay. Well, yeah, we can try it, but I was just.
Let's hope that we're all friends and we do only the good things to each other. Okay. So without K points, things will not work. Well, for most recent version of VASP, it will work. It will assign some default value, but it's not the best. So NSW, there is a concept of partial optimization. If the NSW is big enough, then code will terminate automatically when it reaches convergence. But you may set up this breaker a little earlier, and it will it will be a little less than complete optimization, but still something reasonable, just to save numerical effort. Okay. As we did in the lab, you also need this script. You can copy it from your previous run or from like a template. So core debug 1. This one has like minimal requirements that should go almost immediately to the queue. And to submit into the queue, you just type the command sbatch space and then name of the script. Then, like, I'm always nervous when my jobs do not start running, and it's natural question to see how far they are from running. So one of the ways is type sq is just check, then username, and if I have more than one, I can like grab debug because it is in a debug queue, or grab and put here this number. You don't need it for the homework, I'm just sharing. Or the command sqs gives a list of all jobs you submitted with projected start. So for this job, it was telling that it started in one hour, but actually it started in 5 minutes. It's not precise, and it gives exaggeration worse than it is. There is a version of WASP on the Photon cluster. If you just type, if you create directory, create 4 input files, and type bin wasp dash photon and enter, it will start running. So if you need something really small, like 10 atoms cluster, feel free to do, and avoid these difficulties with big remote cluster. But you will see that it is slow and not productive, so do not rely on it. For projects, you will need to use productive clusters. Okay, so here I'm just copying everything, from NERSC, SCP, space, star, space, to the Photon, to the directory where I want to see it, right? And then I was just lazy to type which specific files I need, like outcar or whatever. I just copied everything. So now I'm back on the NERSC. Some of you did ask for geometries, how to convert WASP output into the XYZ coordinates. So there are specific commands, specific scripts. They are not created by WASP people. They are created by simple humans like we are, users, to help each other to use WASP. So they are located in a specific directory, and this list of this directory is listed among So when you do this model show WASP, it tells everything you need for use it. So this VTST scripts, and they're available on the internet. You just do not want to waste your time if they're predominantly uploaded. And we have copy of them on the Photon as well. So with among the scripts, there is a position to XYZ space contcar. So this command will convert contcar, which is output of geometry in WASP format, into Cartesian XYZ format.
Question.
Yes.
So for that line after the CS4PB, you don't need like cats or anything like that. You can just run that whole line.
Whole line, space, and then name of the file that you want to convert.
I was making. I was putting cat in front of that, thinking that I needed to.
And there is another thing that I personally practice most of the time, x.to xyz.
Okay.
This file while optimization goes, there are several snapshots, and this command converts all snapshots into collection of snapshots and calls it movie. Later on, we will use it extensively for molecular dynamics and for creating actual animations. So, after I have created this contcar.xyz, I can look in it and see that it looks reasonable. So, number of atoms, and then a list of each element and Cartesian projections. Then copy it to the. Then I'm going to Photon and copying this file to Photon and analyzing it. So here is geometry I used before optimization, and here after partial optimization. So moved bromines a little outwards and cesium a little inwards, and then just measuring distances and filling them in. So +10. If you see some images, give credit while you're grading. For the values of the bonds, I did partial optimization, maybe not ideal. So, but distance from lead to cesium is more than 4 angstrom. And they all are about the same. And distances to bromine are about 3 angstrom, so they're a little closer, and there are 6 of them. So if you see similar numbers, just give credit. Okay, copy paste segment of outcar corresponding to frontier orbitals. So you can do it by tail, certain number of lines from outcar. More. And when you see this list of orbitals, you just copy paste the segment that has occupied and unoccupied, right? And the next question is just pull the last occupied, first unoccupied. This number goes here as ionization. This one goes here as affinity, and their difference. So this much minus this much goes in here as gap. And for Fermi, you have figured out that you just type grep Fermi and this number pops up, right?
What is grep exactly?
Grab.
Grep?
Rep.
Grep. Grep. A lot of friends and colleagues were twisting my arms and telling me that I need to study Linux at my first year of graduate school, and I was resisting because I didn't like the command grep, and I didn't know how to explain what it is.
It's grabbing. It's just really grabbing. That's all it is.
So it when you grep Fermi outcar. So this command reads the file and looks for a word inside a file. Like if you feel file like my name is Mead, huh?
Yep.
So and then you it will be like file, and then you type grep space is and then file. It will answer is.
So grab is from that file.
So it recognizes pattern inside a file.
Okay.
Okay.
So you didn't like that, huh?
Oh no. So, in order to make density of states, you do need states file. You can either manually copy paste it from screen, or there are auxiliary programs that help to extract it. For this extractor, you need, so here is the extractor that reads outcar and creates energy pop. So, but in order to use this extractor, you need to know how many orbitals you have and list them. First orbital, last orbital, and then just service number 1. And then after you run it, you need to copy this energy pop into states. plus 10 plus 1 plus 1. So report number of lines in file states. If you're not sure, do WC space states, and it will show how many lines is in the file. This is needed to avoid error in the subsequent code. Then number of electrons in the model. This is needed for normalization, how high is the density of states, because you may want to compare models cluster with 10 atoms and with 1,000 atoms. And then if you do not do normalization, they will be like 100 times different in amplitude and hard to compare. Number of ions, good. Well, whatever, 0.01, okay. 0.5, not full credit. And then you execute the code that converts the file states into file DOS, right? So it asks number of states, you give number of lines, then you give the range in which you need to explore. So start in electron volts, and this is Fermi energy in electron volts, and this is parameter. We will not discuss what it means, but alpha plus beta from the same line as Fermi. Then it asks for width of line. If you need, you may play with this, but right now you just give name. Magnitude, just put 1 and do not worry. Number of atoms, number of electrons, gap. You may change this number, but nothing will it's redundant from previous version. So if you have this record DOS Fermi is written, it means you have numerical data for DOS that you can plot with either GNU plot or Microsoft Excel. Report size just mean list is ls minus ot. It gives the number of like 279 kilobytes. Which version? So in the binary there are several versions of this scripts to convert the DOS Fermi file into graphical. So you run it, you get this DOS PS, you convert it somewhere PS to PDF, right? You convert it into PDF, and then you send the files from the NERSC to the photon, to the directory that you have chosen to work with. And then you look on the density of states. So some, like if the why this homework is so ugly and long. If I do it blindly, like if I would get this assignment, I would focus only on density of states and forget to check geometry. And there is I'm not showing it, but I did a couple of attempts where optimization went in the wrong way and created ugly structures. If the structure is ugly, the density of states may come like going occupied orbitals to energy of 20 electron volts. Or we know some people who recently did it. One can get gap in the reasonable position near 0, but it can be very narrow, like 0.5 electron volts, which is not right for this material. So here one has band gap of slightly bigger than 3 electron volts, which so this material in bulk has around slightly more than 2, but this is increase of the gap due to quantum confinement. So it looks reasonable. So if you're grading work and see something like this, give full credit. Which orbitals are occupied? Well, those with energy, those which are indicated by these red areas. So if you used right versions of codes, it will mark occupied orbitals with these field areas. If you do not see these field areas and you do not see this answer, withdraw a couple of points, just to remind it to the author. Based on those image, estimate gap. Okay, about 3 electron volts. Plus 10, plus 10. And then please add together, or do the same thing for, I do not have grading key for second part, so I'm getting zeros for myself. But you can go through work of your classmates, try to give bigger credit. I will collect it.
Oh, you
Mm.
like it, okay.
I will collect it.
I
And-
tried.
So please add together all numbers and put it on the top of the
I
front
put it
page.
in a box.
Okay. Did you add together? Yes. What? That's good. That's good. Well, do you add together?
Oh, yeah.
Put it on the front top.
Just add them up.
If you want to start, we do the number of points and then divide it by 200. So those who get not large number are impressed. Keep benefit of the doubt. They all are humans, we should think broadly and friendly on whatever people are doing.
Could you just want VP? Lay down the hand. There's no 3?
I will just make quick. So I will quickly make the quick scan of this front pages. Thank you. And those who submitted 2 copies of homework get double credit.
Huh?
Those who submitted, I'm joking. Those who submitted more than 2 copies of the homework get double credit, right? For
What
return.
ones were, you didn't have to find those ones.
Oh, well, I have 2 scores, one with the one that went from the phone.
Oh, okay, good, yeah.
So I didn't know what you wanted.
What was the one without the black ones? Deviate ones with the ones, just the right question.
So I had to.
So the idea is that we'll get more confidence and practical skills, and more. And also, you are getting very generous credits for your, through your presentation. So it's these grades are more like assessments of the learning curve to see if you are performing perfectly or a little.
Okay.
Yeah, no, this is the other one, me too. Theoretical structures.
Oh, also he,
Yeah, so it's my other.
okay, so I didn't know.
Take.
I have two words without names.
I'll take one of those, fine. I'll take one of those.
Maybe it's not.
I'll
Put
take
it
one of
on,
them.
let's put it on the credit list.
Oh, give me those with more credit.
What the- Now that it's this one.
Okay. So I'm giving heads up of how the next homework may look like. So we will do the periodic model of the titanium dioxide. And for extra credit will be 3-dimensional. Okay. So before we, is there an advancer? It work? Yes. So we all are well familiar with Hartree-Fock. It's not impressive. You all know what is plane wave and how the matter interacts with how the light interacts with matter through this dipole interaction, right? Dipole times electric field, and generally now lean back, relax. It will be not part of homework. It's just general mumbling for general context, right? So if we look onto actual molecules, we need positively charged ions and negatively charged electrons, and then we have the dipole operator. And if we consider optical excitation, promotion from occupied to unoccupied, generally it is multi-electron problem. But on the last lecture that some of us missed due to celebration of the coming break, so there was a discussion that multi-electron nature of the of this transition dipole operator in an actual molecule can be reduced to a matrix element in basis of one electron. And we did it meticulously and came to the conclusion that just matrix element of position operator between initial and final orbital is a very good approximation to describe how intensively molecule responds to optical excitation. So we need to consider periodic systems often where the so-called unit cell, simulation cell, is enclosed into imaginary box, and this box is repeated. And in each of the boxes, the image is the same. This gives specific signature to electronic structure. I understand how bad this blinking, but I will send the slides. Do not do it for you. So if the potential defined by ions is periodic, then electronic wave function has periodic main portion localized on ions times accumulated phase, which will be different at in each periodic image due to possibility that electrons, even in ground state, have non-zero momentum or wave vector. And relax, no new material, it's all was before. and the total energy of electronic system is adding together energies of occupied orbitals up to Coulomb plus Coulomb and exchange terms. But if one neglects this Coulomb and exchange term, then, so it's not quite correct, but it is a reasonable approximation for initial assessment, so that energy difference between models that are ionized by removing or adding an electron approximately equal to orbitals of energies of orbitals of Coulomb and Luma. This is called the Kuhlmann's theorem, and the homework that you just completed and graded was based on this. So you just report energies of orbitals and tell that they are as good as ionization and affinity. Okay, so what are we going to do today? Oh, this is approximate subjects for your presentations. We are not electing them yet because we still need to go through some things in the lab. So we are starting the new subject of so-called density functional theory, and it has historically a lot of scientists were declining and telling this density functional theory is not a theory, it's like chemistry and alchemistry. So same as some people were declining quantum mechanics when it came. So the goal, narrow goal of computational chemistry is to get total energy of a molecule composed of so many ions and electrons, right? And all mechanics, how we get this total energy, is secondary. Before we used methods that are based on wave function. In fact, we went through only through one method, Hartree-Fock theory, but there is a big family of methods that are of the same nature and are built upon Hartree-Fock theory. So they use concept of wave function to get total energy. There, if you are, like now you can wake up if you need very, like in 2 figures explanation what is density function theory. This is a procedure that allows to get total energy of a molecule based on the positions of ions, but it doesn't use concept of wave function. Instead, it uses concept of density, which is wave function squared. How the charge clouds are distributed. Not wave function, not not wave function, but charge density. This is substantially simpler. This is it gives speed up of any calculation. And there are theorems proving that this is possible and this is correct. And by today, density functional theory is a workhorse of computational chemistry. You cannot be super competitive with high precision, like some people in the audience are. Yes?
So charge density is basically coulombs per meter or charge per distance?
Distribution of charge. So it's, I would say it's Coulomb per
Okay.
angstrom squared, or elementary charge per angstrom square as function of position. Okay. So there are a lot of methods that give much better high precision results for observables, but the price for computation scales very nonlinearly. So even this theory is not new. The theorems were introduced in mid-60s, and the reliable working codes were introduced and tested at the beginning of 19th. So it's like almost 30 years old, or even 50 years old workhorse, but it is a very good starting point. Before applying any advanced methods, one may test any model or material with this density functional theory. So the plan for getting through the theory is as follows. So we'll get through some definitions. There will be background theory that those of you who were exposed to some level of quantum theory, either basic quantum mechanics or advanced quantum mechanics, may have seen. So we will cover so-called Fermi gas of putting a lot of non-interacting electrons in the big box. So it has no relation to real world, but it is important intellectual step. Then there will be two theorems that right now we do not need them. No one will ask us to prove them in public, but you need to be aware of them to be confident that what you are doing is not wrong, and when you present on conferences or publish papers, so that there is a level of trust to density functional theory. So it's not fantasy, it's based on rigorous theorems. And then there will be practical algorithm similar to flowchart for Hartree-Fock theory, and then we'll mention observables, same as we did for Hartree-Fock. Right? So it's a plan for several weeks. So here I'm celebrating my laziness and lack of wish to really write it with type these equations. So what is density? If you have orbital star wave function conjugated with wave function itself, you'll get density, right? So most people, through standard interpretation of quantum mechanics, tell that it is probability density. But there was an interpretation that it's not probability density, but it is charge density, because wave function is for electron. It's a philosophical question which is not healthy to discuss. But if we can cynically use one or another approach depending on our benefits. So for density functional theory, believing that wave function squared is charge density is very useful. So if you have one electron, if you integrate over the whole volume, you get one, right? So density functional theory. We know what is density, we know what is theory, now we need to know what is function. You do know what is function, right? So mathematically, what is function?
It's it describes what happens to each. It's the position of all your.
It's like connection, correlation between one, well, general and several, but between argument and function, right? So you have, when you do plot experimental data in Excel or with GNU plot, you have two columns. One is X and another is Y. And between these two sets of data, there is a correlation. For each X, you have certain Y, right? So functional is when you still have one Y, but it is for very many arguments. Like if there is not one argument, but like 1,000 arguments give you one function. So instead of argument, you have the whole function. And this function takes different shapes, and as a result, you get one number. So basically, this operation of integration of charge density over the whole space. So charge density is a function, you integrate, and you get number, typically 1. It is an example of function, right? Well, it's a little ridiculous and simple, but formally, yes. And if you have more than one electrons, you have first electron, second electron, third, each in each specific orbital, with each specific orbital distribution squared. And then you can, if you add them together and integrate all of them, you get, so integrating each orbital over space will give 1, and if you integrate all occupied orbitals over space, you'll get just number of electrons, right? So if you formulate this charge density of all electrons in a system, integrated over the whole space, you'll get number of electrons, right? So it's another example of a function. And we're not going into rigor. It is just getting a little taste and flavor before we get further. And there is a notation accepted in the community and literature. So when you introduce function, you use round brackets. When you use functional, you use square brackets. Well, not everywhere, but in computational chemistry community. So, number of electrons is a functional of charge density. Rectangular brackets. Okay. So if you are impatient and want like quick, give me something. If you put instead of n, we put energy, then it will be basically density functional theory. How to get total energy as a function of charge distribution density. Right? So we do not need another month of lectures. Yes?
So functional and the words functional and function, they both mean the same thing.
Function typically is like one function of one argument.
Okay.
Or maybe like two arguments. And functional is one function of infinite number of arguments, of the continuous function. Like functional function.
So a functional is a function of a function?
Yes.
Okay.
I never heard like third order functional, like functional, but maybe it does exist in formal math. So do I really want to tell it right now? It's a little. It's not super challenging. Okay, I'll start and you'll tell me when you feel tired. I'm already feeling tired.
So dealing with that function of a function.
Yes, I'm
Oh,
hearing, listening.
I'll wait. If we had a function
Please split and distribute.
of a function, are you saying it's kind of like the idea of like you press the gas pedal to move the car?
Whoa. Just let. I need to carefully listen to.
To clarify with the function comment, are we saying it's like you press the gas to move the car?
Press who?
Press the gas. The function of you pressing the gas moves the car, and then, but the function of the car is to move you. So is that kind of like the layer of a function that you're trying to discuss?
I would avoid this logical connection.
Okay.
Because we use the same word. There is ambiguity. There is a like function of a faculty is to write grant proposals.
Yeah.
It's the same like function of a car to move the body of a right person. It's one meaning. And another meaning, the position of a car in space is a function of time. It's just connection, correlation between two sets of data.
Okay.
So it's you see there are two meanings but one word. So Thomas Fermi theory of ideal gas is a background, and I'll try to do a little bit of it, but you already invested a lot of energy into homework, so we just need to do something so that we do not waste time next. So, this is a little, I wouldn't say boring, but useless theory that used only as intellectual step to get flavor of what is functional in a little bit more practical sense. So, those who took, it's not Ben now because Gage is not here. In introductory quantum theory, we considered a fantastic universe that contains only one electron, right? For basic quantum mechanics, it's the nature of the thing. For free space propagation, right? And this one electron was not interacting with other electrons because there were no other electrons. Now we are getting a little upgrade. we will have a universe that has 3 dimensions, and it has more than one electron. But these electrons suddenly forgotten that they need to repel each other. So they just like blindly smash through each other and do not collide. So it is just space, 3-dimensional, with large number of electrons, but those are stupid electrons that do not interact. Okay? And for this crazy universe, there are relatively simple mathematical consequences that look approximately like density functional theory. So this theory was made in about the same year or a couple of years later as quantum mechanics Schrödinger equation was designed, and it was used only as like homework assignment or like toy for mathematicians. But later on, one realized that it has connection to DFT as intellectual step. So if we have our universe, well, not our, but this universe with non-interacting electrons, we may practice principle of ancient Romans, divide and conquer. And it is the simplest way is to divide on boxes, rectangular boxes. So we split universe on rectangular boxes of specific size. Like length of the square box is L, volume of a box is L cubed, and elementary volume is elementary volume. Then there is total n capital of electrons, and in each box we have delta n electrons. So we evenly distribute all electrons over all boxes, and we don't care what is exact number, like 1,000 or million, evenly distributed. And the idea is that total energy of all electrons in this universe will be summation of energy contribution in each box. Like energy in one box times number of boxes, or just add them together if they are not equal. And the question is, so there is a little symbol missed because of this video. So is it possible to formulate this piece of energy in terms of number of electrons divided by elementary volume, delta n divided by L cubed? So if it is possible, if any logical steps help us to do so, then it will be like density functional theory for fantasy universe without molecules and non-interacting electrons. So please raise hands if you never practiced this particle in the box. It's really. Right? Okay. I'll tell you a joke so that you do not fear particle in the box. One of the persons who is very close to me was writing a PhD thesis once and hired a professional editor to check the language. So the professional editor was not a science major, it was just linguistic major. And then this person who got money to read and debug told them, okay, not bad writing, but here there is a mistake. As a English expert, I tell you it's wrong. You are writing that you are considering particle in a spherical box. It cannot be so. You need to write particle in a spherical container. So there are no so particle in the box is a colloquial term, and if you were exposed to it, you know why. If you didn't, basically it's one of the very few problems that can be solved, quantum problems that can be solved analytically without any computers. There are like a handful number of such problems. And like free space, particle in the box, rigid rotator, harmonic oscillator, and hydrogen atom. All other things need approximations or computation. So the one-dimensional box with one electron is famous because based on the size of the box, one can get a set of orbital energies, right, and shapes of orbitals. And if one gets into 2- and 3-dimensional boxes, the solution doesn't change much. So for 1 dimension, energy of orbital number mx is same as in classical mechanics, momentum squared of the mass, and by specific conversion of momentum from classical to quantum operator and this quantization, one gets the equation of the quantum number squared or the size of the box squared and some constants. So energy of an orbital is a square of a quantum number. It's not always correct. It's only for the box. For other systems, it's different, right? So quantum mechanics is solved. No. Right? So it's a big benefit. And if you have 1 electron in 3-dimensional box, then you have 3 quantum numbers, right? Quantization along each axis, x, y, and z. And then the energy of quantum state is labeled by 3 quantum numbers and is function, no functional thing, function of these 3 quantum numbers, and x squared and y squared and z squared with some constant. So you know everything about energy of each orbital. Those who took, Ben was practicing the boxes of different shapes and looking how the quantum confinement changes density of states. What do we think when we look on this expression mathematically? Which ideas, which thoughts visit you when you look onto this equation, on this part of the equation?
Reminds me of a squared plus b squared plus c squared.
Yes, which is?
Well, if
Let's-
I solve for c, it's the dimension, it's
like
right?
pyramid, I don't know. But
It's
what?
Pythagorean theorem is what it is.
Huh?
Pythagoras' theorem.
Yeah.
Okay, it's one thought close, but another
It's your
thought.
volume.
If yeah, if you replace a, b, and c onto x, y, and z, x squared
It's your
plus y
coordinates. It's your coordinates in 2-dimensional space.
3-dimensional.
3-dimensional space.
Z.
Sorry.
Show me. Yes, Sudipta?
So you probably show me.
Yes. Look on Sudipta. Repeat.
It's a 3-dimensional, how to say, okay, so
It's a sphere.
Just
it's kind of like this,
Uh-huh.
so ellipsoid, 3-dimensional.
Okay. Yes. And generally, if you write like x squared plus y squared plus z squared equals like 1 or r squared, it is a equation of a surface of a sphere, right?
Yeah.
Okay. Then it looks like radius, distance from origin to the surface of a sphere. But now we are in a space of quantum numbers. So it is a radius in a space of quantum numbers. Right? And in some sense, energy of quantum state is a function of this r square of a radius in space of quantum numbers. Right? So we replace this and x square and y square and z square by r square and some constants in front. Okay? Like projections, distance from the origin. Now, what is our goal? What are we going to do? So our goal was to find total energy of this universe as a summation of total energy of all boxes. And each box has delta n electrons. And size of the box is L lowercase. So we need to know the energies of all orbitals, populate them with electrons, and multiply each occupied energy, occupied orbital by its energy, and add them together, right? Same as you find momentum, like occupation times energy, occupation times energy, and then you'll get total energy. Same as in Hartree-Fock, if you remove the Coulomb exchange. Okay? So let's quantify it and look. So we will need make connection between number of electrons that have energy in a range from with quantum numbers radius goes from 0 to r. Or as a simpler task, how many, what happens if quantum number radius stays within very small increment from r to delta r. So we are trying to overcome mechanistic details of what is the specific value of an x and y and z, and just take them all in a certain slice. So we look like a little shell of a globe, or a little shell of a spherical egg, or whatever. Right? So the question is how many states will be localized in this infinitely thin layer, right? So if our box sizes are equal, then quantum proportionality coefficients from contribution from x, y, and z will be equal. So to find the amount of states in this thin shell, one can practice equations for like volume of a sphere, right? And then so volume of a sphere. What's the volume of a sphere? Huh? How many?
4 times pi r.
Yes. And what is the surface area of surface of a sphere? If you yeah,
No,
but if
that was-
if you do not remember it, how do you derive area of surface of a sphere if you do know the volume of a sphere? Huh? The first letter was correct, D. Yes. So the area is derivative of volume. Right? Derivative of volume in respect to radius will give you surface. And if you need infinite, so
No.
no, yes.
No, I agree. I was saying that.
Okay, and if you need the non-zero thickness shell, you multiply surface area by dr, right? Right? And through taking derivative, this constant disappears. So 4/3 pi r third, and when you take derivative, third power converts into second power, 3 comes up front, and then it cancels with this 3. And then you get 4 r squared dr for the volume of the thin shell. But it is not a real space, but space of quantum numbers.
So r squared is equal to nx squared plus ny squared plus nz squared?
Correct.
Okay. And in 4 pi r squared dr is the difference in the volume of those two shells?
Mm-hmm.
Okay.
we put factor 1/8 up front because we are considering only positive values of an x and y and z. So if it is planar, it is quadrant. If it is three-dimensional, it is octant, right? So number of quantum states in this thin shell is a function of this quantum numbers radius. So number of states. Agreed. Now, we need to connect two things. On one hand, we do have equation for number of states inside the sphere. On another hand, we do have connection between energy and this quantum number radius, right? Is there a way to recast all equations in such way so we forget about this R capital variable and speak only about energies? Can we like remove unnecessary things? So if energy is a square of this quantum number stuff, right?
We can just plug in.
Then this radius is square root of energy, right? And then radius here can be plugged in as a square root of energy. And then you get power 3/2. So if we plug it in here, power 3/2, it will be number of states with energy equal or smaller than this epsilon. So you are so advanced. You are browsing in a space of quantum numbers and making some geometry in the space of quantum numbers. Okay, and our goal is to find, to make a connection between number of electrons, volume, and total energy. By now we have number of states. What else can we do? So what is the derivative of number of states over energy? It is a concept that we all are so happy with, and we were and we will do it every homework and every lab. Derivative of number of states over energy. Huh? Yes. Well, it's not a big intrigue. I think it should be written somewhere here. No? Okay.
Well,
Plus one credit to that. Density of states, right? So density of states, on one hand, practically, it's summation of these little delta functions as we practically implement. But formally, it is density is derivative of number of states as function of energy over energy, right? And if we apply this definition to our number of states in our box, number of states that have energy equal or smaller than epsilon, and then we take derivative, our power 3/2 gets into power 1/2, right? So we are getting density of states, density of quantum states inside a box that is part of the universe. Good? Some of you are yet following. And Ben may remember that it was one of the, I should insert here the movie next year. When we explore density of states for three-dimensional box, if the box has equal sizes, it will be this power 1/2 as function of energy. If it is like quantum dot or nanowire or thin film, it will show specific signatures. Okay. So our goal is total energy, And by now we have total number of states of specific or smaller energy and density of states for one box. What is shown here? Who recognizes this image or this equation? 1? Okay. 2? So what is it? Yes. So Fermi distribution. Some of you were asking what is Fermi energy, right? So Fermi energy was introduced much earlier than density functional theory as a concept. So if we assume any model that has many electrons, right? Many states, many fermions, there is a some of you have taken statistical mechanics and thermodynamics, right? And you know about Bose-Einstein and Fermi statistics, right? It's not a big wonder. Okay, so electrons as fermions do have a feature that each quantum state can be occupied only by one electron, right? And they by like minimum of energy they start filling states with small energy first, and then when we fill states with like negative energy, fill, and then we are getting rid of electrons. We do not have any more electrons, and states for energy less than Fermi are occupied. States with energy more than Fermi energy are unoccupied. It's same as we see in this homework that we just went through. So everything below energy has like 2 electrons because spin up, spin down. Everything above has 0 occupation, right? But this occupation may differ from discrete numbers. It can be not only 1 and 0. It can be fractional occupation. And this happens if system experiences thermalization. Then in the region where we go a little below and a little above Fermi energy, this distribution gets smoothering effect. That comes through this equation. It has temperature as a parameter. With 0 small temperature, it looks like a step function, and if temperature increases, the curve becomes smoother and smoother. Okay. But the only thing we need is that one needs to introduce occupation function. So, like, we do have states at certain energy with certain density, and some of them will be occupied and some of them will be unoccupied. How do we quantify? How do we mathematically tell which are occupied, which are unoccupied? So if we are not material scientists, chemists, but like abstract formal mathematicians, we do not care where the states convert from occupied to unoccupied. We just tell formally there is an occupation function that tells at which energies orbitals are occupied, at which are unoccupied. You can call them by letter F. Then we multiply our density of states by occupation function. Everything below Fermi energy is occupied, everything after is unoccupied. Good? Density of states. And in our images and homeworks, we have this like field and this unfilled. Okay? You see little connections. So if we need to find total energy, we need to add together energies only up to here. So to make integral of this curve only here, multiplied by value of energy, right? So this is the standard way how one computes first order momentum. Momentum not in the means of like velocity, momentum, but momentum in mathematical sense. So distribution times first order of the variable and then integration. So if we need to find energy inside this box, we integrate density of states times occupation function times energy and integrate over energy from 0 to infinity, right? And then since this function becomes 0 after energy is bigger than Fermi energy, we can stop integrating at Fermi energy. So we are integrating not from 0 to infinity, but from 0 to Fermi energy. And then we get rid of this f function and just multiply energy times density of states integral over energy, right? So this will be a protocol to find total energy inside of all electrons inside one box. So through consideration of the particle in the box, we have density of states, and here we have equation for momentum. And if we forget about constants, so density of states is square root of energy to the power 1/2, then multiplied by E, so it will be energy to the power 3/2, and then we need to integrate over energy. So integration lifts the power by 1, right? So integral of E to the power 3/2 will be how much? Huh?
5/2.
Yeah, correct, 5/2. And then we, since it is a definite integral, we need to evaluate this integral at the limits. At lower limit, it will be 0, right? Because E to the power 1/2, 0 to the power 1/2 is 0. At the upper limit, it will be Fermi energy to the power 5/2, right? So energy of all electrons inside one box will be constant Fermi energy to the power 5/2. But it is not sufficient. We need to add together all boxes, right? One thing. And we need not only energy, we need volume, we need density. So we need to formulate total energy as function of density. So can we express number of electrons inside the box in the same way as function of Fermi energy? Yes, if we remove energy from this, if you like, find 0 order momentum, right? Do the same integral. So we still integrate from 0 to Fermi energy of density of states without epsilon here. So we need to integrate E to the power 1/2. Integration lifts up the power by 1. What will be the answer? E to the power 1/2 plus 1. Yes, correct, 3/2. And then, we skip constants. And then we need to, again, evaluate it at lower and upper limit, from 0 to Fermi energy. At lower limit it will be 0, at upper limit it will be Fermi energy to the power 3/2. So now we do have number of electrons inside the box is Fermi energy into the power 3/2. Total energy of all electrons inside the box is Fermi energy in the power 5/2. We are very close. So we have delta n. We have the size of the box L, or volume L cube as a parameter, and we have total energy. So we need just to add this all things together. So we merge together these two components. So if the total number of electrons is 3/2 of Fermi energy, can we invert this function and tell how the Fermi energy depends on the number of electrons. Just formula. So if the number of electrons is 3/2, and we invert it. So if we take number of electrons into power 2/3. Do you follow it?
The math, yes.
Okay, 2/3. So Fermi energy is just number of electrons inside the box in the power 2/3. So now we do not have this outside parameter. So we have redefined Fermi energy just based on the number of electrons, right? So we, wherever we need Fermi energy, we can plug it in through this. Here is the delta n to the power 2/3. And if we need total energy inside the box, we need to have 5/2 of this Fermi energy. So we need to take delta n 2/3 in the power of 5/2. So this is Fermi energy, and this is total energy. So if we do the math of this combined powers, it will be that energy of all electrons inside the box that contains delta n electrons is delta n to the power 5/3. You didn't catch me lying, because I wasn't, right? So in case we believe that there are no ions that attract electrons, and there is no repulsion between electrons, then we are almost arrived to the density function of theory. So the number of electrons inside the box determines energy inside the box. And the only thing that we need to do is to integrate over the all space, all universe. So instead of this delta n, which depends on our L parameter, we may introduce the density, which is more continuous. So we divide this delta n by volume, but then in order to keep mathematical equations, we must multiply it by V. So volume element by density will be the same as delta n, right? Same as in middle school Archimedes law. So here we divide delta n by volume, which is size of the box to the third, and in order to keep equation correct, we need to put the same power of the volume outside. So volume to the 5/3 in the numerator and denominator. And for simplicity, we can forget about this stuff and think that we have a good constant that includes this place with size of the box. And this delta n over L third is density. So energy of infinitesimal unit, infinitesimal box with density rho of r is rho to the power 5/3. And now the remaining thing is to integrate over the volume, integrate together all boxes. So we need to take this rho to the 5/3 and integrate it dx dy dz or dv, right? So integration. Why I'm not completing? Why I'm not doing this integration in a final result. Why I'm stopping and not doing this integration? Because originally we decided to think that electrons are homogeneously distributed. But this expression doesn't require homogeneous distribution. We can have parts of space where density is higher, parts of space where density is lower, but the equation still will be correct. So we need to take density defined in all portions of space, take it into the power 5/3, and integrate over space with some Fermi constant. So it is a functional of density, right? It's not function, it's functional. Because you take this function and integrate it in order to get a number. And it gives total energy of system of many electrons. Of course, it is not practically useful. We cannot use it for our real life, for molecules and materials. But it gives general idea how the density of electrons can be connected to total energy of a system. Okay, Thomas Fermi theory. You have seen the abbreviation LDA, right? Local density approximation. When total energy depends only on density locally in each point. And often in practical life, it also depends on some corrections, like on the gradient, on derivative of the density in the nearby vicinity points. Then it is GJ functional. So Thomas Fermi theory doesn't replace DFT, but it gives us first step towards flavor what it is. So Thomas Fermi theory is lowest level of LDA, if so to say. And my favorite slide. Thank you for your patience. Relax, get done with your other classes, accumulate energy for next evening. We'll get through boundary conditions, absorptions, and all that.
And you know that mine are two separate copies, right? Because I have
Yes. For your grade, either take largest of those or.
Okay. I'll retrain.